Hello, everybody. Hello. Good afternoon.
Hello, Bernard. Let me know when I should start.
Can you already start?
Oh, yeah.
Okay. Okay.
Okay, so I can share my screen.
Well, let me share my screen first. I will give a very short introduction to the session, then continue step by step. So very warm welcome from my side. My name is Bernhard. I'm an innovation manager in AVL, and together with my colleague Oyana from Enrichment, I'm very happy to organize this session on automotive today, a session on automotive and its relation to big data and data management. Me and Oyana, we are heading this group of activities. We are doing this group of activities regarding the automotive, the role of data in automotive within BDVA. And well, we have compiled a program for you today that hopefully you will find attractive. So we will have a couple of speakers today. I'd like to start with Deepen AI. The company, Nicola will report here, will give us a talk on data challenges for automated driving systems when it comes from the transitions from data from the sensor to recording of valuable information. Yeah, and then we will continue with a topic related to cyber physical systems, the CPS for EU project, and it will be about pre-integrated architectures for the cyber physical systems. And Philippe from Valeo will give us some insight on that. And then it's a pleasure for me to announce that we managed to initiate some kind of cooperation with another task force in BDVA. Namely, there is a task force on mobility that is guided by Intrasoft, and Vivian has organized here a very, very interesting speaker, Roberto from University of Modena, who will give us some insights on autonomous vehicles and smart cities, particularly in an area called Motor Valley. So I very much look forward to that. And finally, we will turn to the topic of connected, cooperative, and automated mobility. And it's a pleasure for me to welcome Stepan from Ertico. He will then give us some insights on challenges and future research and innovation needs for data sharing in this field of CCAM. And finally, my colleague Oyana from Vicontech will conclude on the Cluster 4 partnership on the cooperative and connected automated mobility. And therefore, let's say I don't want to lose any more time, and I suggest to start now. I would ask the speakers to somehow fit to a slot to 20 minutes. Audience can post some questions to the B2Match platform. I will have a look at the B2Match platform and try to moderate these kind of questions that pop up so that we have the chance to have some answers to these questions after the talks have been finished. So thank you very much for this, for participating here. And it's a pleasure for me to start with the first speaker from Deepen AI. So Nicola, the floor is yours.
Thank you. Thank you, Bernard, for the introduction. Let me share my screen now. This should be, I hope you can see my slides now in presentation mode. Is that the case?
I can see it very well, yes.
Okay, perfect. All right, so just a quick intro. I'm Nicola Croce, I go by Nico. I'm a technical program manager at Deepen AI. We are still a startup, I would say, based in Santa Clara, in California. And we are basically building software tooling to help the development of autonomous driving systems. So we're active mainly in 3 pieces: calibration, annotation, and validation. And we'll see later a bit more of, in the end, what we do. The focus of my talk today is going to be on the data challenges for automated driving systems from sensor data to meaningful information. So starting really at the source and then see how there are multiple challenges along this whole pipeline, let's say. So in terms of journey, we are going to start from really having a bird's eye view on this data pipeline for ADS development and see where the data comes in and how it is being manipulated and enriched, and then also how it's fed back into this loop. We're going to see and touch on about which are the data integrity challenges that are right at the source, and then which are the challenges where we need to augment and enrich the data with meaningful metadata that helps this system to understand the world or do basically actionable things with the data coming from the sensors. We'll touch briefly on the topic of standards, just because, and in terms of standards, format, and interfaces, just because is a central topic in order to basically close the loop and enable valuable use of data at scale. And then directly related to that, there's the topic of data sharing, and we see how these standards enable data sharing, and also we'll see how about some of our initiatives in that domain, which are purely community initiatives to help all the stakeholders advance into the safe deployment of this technology. And finally, a brief summary of what we do at Deep. So starting from the data pipeline for ADS, usually what happens purely from a data perspective to be able to, let's say, build safe autonomous driving systems, specifically machine learning based systems. So we're touching a little bit more on the, if you look at the traditional stack, on the perception and prediction pieces. We start from data collection, and this is something like, this is probably a step which is a little bit underestimated, in the sense that a lot of what happens after is really conditioned on how good is this data collection being performed. So we're going to touch on, we see that there is a very important piece of the story here in avoiding, let's say, the garbage in problem and ensuring data integrity. And then we move on into, once this is done, we move into building the ground truth, which is used normally to train and test in the machine learning models, mainly for object detection, tracking, and so teaching and training this system to perceive the world. So with this ground truth is exactly used with this scope of AI model development, mainly, or validation of sensors or any other, let's say, piece of the stack. And then sometimes we feed back into this loop of informing the next stage of data collection with the holes or things that we discover throughout the whole journey, in order to optimize the data collection for meaningful information again. So let's see the first piece here of avoiding data integrity, which is very fundamental, because a lot of times what happens is that basically we underestimate how crucial it is to collect data very well at the source, at the beginning of the plan, meaning that we need to have very proper calibration in place and synchronization across time and space. Because if there are misalignment in one of these three, let's say, dimensions of calibration, synchronization, and localization, this can affect very badly anything that goes anything in the downstream, let's say, pipeline of data. And it's very hard. It becomes also very hard to produce high quality ground truth and high quality labels to then train the models. So it's really crucial to have calibration fixes between 3D and 2D also. So it's not only talking about the intrinsics of the sensors, but also calibrating multiple sensors together, even of different modalities. So we saw how the multimodal nature of data sets now that are also open and used is increasing. There's a shift towards multimodality, and this calls for a very precise calibration, let's say, across different sensors. which is not only through space, but also through time, because it's very important to fix time alignment in the different sensors. And even when some of these sensors are very difficult to match, right? Because sometimes you can have this flash LiDAR that has a specific pattern, and you have other LiDARs to synchronize with, and a camera. So it's very crucial to get those things sorted at the very beginning of the data collection campaign, so that we avoid basically problems downstream. And so, and of course, once these two are in place, also localizations and fix the drifts becomes easier, let's say. And this is also a crucial piece to have in place to ensure the next step, which is good ground truth. So after these data integrity checks are performed, we move into the so-called data enrichment. So most of the times there's a lot that we can do, but there's not there's a lot more that we can do if we label this data, if we generate metadata that basically tells us about which are the objects in the scene, the action they're performing, etc. So we need, of course, very high quality data enrichment and labeling in order to ensure a safe perception system, right? So this is very important. And in order to have this in place, of course, these three things need to be there. So what are the different ways to represent this information, let's say, in the data? There are multiple ways, and all of this comes with some specifics, nuances, limitation, and pros, let's say. In the market, what we see, being at the data labeling company first, is of course a lot of bounding boxes, both in 3D and 2D, which is traditionally easier, let's say, a more simple way of basically labeling data and building ground truth. And also it comes with a much more advanced, let's say, state of the art in the perception, in the detection models, etc. But there are some, of course, some entities, some things that we might wanna be able to convey to our system that are not easily enclosable in a box, for example, like, I don't know, exhaust coming out of vehicles, or road, pavement, or anything that doesn't fit in a very specific volume. So we need also we need to be able to produce very accurate semantic segmentation, even in 3D, so in point cloud across long sequences. And we need to be able to build and to fuse all these sensor modalities together to build a consistent word representation and word model across all these different sensor modalities and across all these different, let's say, construct that we use, geometrical construct that we use to represent these semantic concepts and entities. So this is also what we call 4D data, because we not only need to build consistent representation at individual timestamps, but we also need to be able to smoothly represent and basically track things over time, how they evolve, and build consistency in the past and in the future, of course. So this also calls for a more, so the recent advancement, let's say, calls for a more advanced and refined way of encoding this information. So we see more and more, not only the traditional, let's say, object labeling, where you need to detect stuff in the world, but we need also to be much more smart and refined in what we label and what we build our models for. So for example, there's a lot of context labeling that is very important to have in place. And this contextual labeling is usually at a much more high level in terms of semantics. So, and it's performed to basically find specific instances of or scenarios in the data. So you might want to be able to retrieve among the data you collected some specific logs that are in the rain, or that have been in urban, rural road, etc. So these are all things that also need to be in place. And the third is building more semantics in the data set. So not only objects, but also the actions that these objects are performing, the events that they are going on. For example, We need to label the fact that this specific actor is performing a lane change at this point in time, and then it's going back to his own lane, so it's kind of an overtake, etc. So we see more and more of these requirements, and it's very important to be able to represent this consistently and label this and generate this ground truth in a very high quality manner, which naturally basically builds a problem in the space, which is a lot of the companies and the organizations working in autonomous driving or automated driving system in general are doing all of these steps, right? Because it's the usual, let's say, journey that we have, specifically with the traditional perception, prediction, planning, control stack. The problem is that everyone is building different representation of the world with different formats, different labels, different ways of encoding this metadata and serialize it into files. So this comes with a lot of limitation in reusability of data sets, maintainability of the data sets, composability. So if I have a data set that I labeled last year and now I need to change it for a little bit of different tasks, it's very hard to do that. And it's very hard to also take an existing data set, which is, I don't know, in COCO format and port it to nuisance format and whatever else. So there's a really bottleneck there in data sharing that we need to address through standards. So this is also something that we at Deepen are really taking care of, in the sense of, and we are one of the shapers of this standardization landscape, which we think is very important, not for us as a company only, but for the whole community to be able to proceed and basically move forward the safe deployment together. So specifically, there's a set of standards that are really helpful in order to basically transform pure data into meaningful information at scale, which is really the bulk of the talk today. And one specifically is called Open Label, which has just been released by ASAN, which is exactly the standardized data model and JSON schema for multi-sensor data labeling and scenario typing. So everything that I talked to you about, so this labeling, tagging of this context information in scenarios and etc. in action, is finally being standardized and provided to the world as a common data model that everyone can use in order to build better data sets, more high quality data sets, and which are easier to share. And this is also being designed, in such a way that we detach basically the semantics from the pure data structure of the labels, so that we point to this OpenX ontology, for example, to deal with everything regarding semantics of this is a car, this is a train, this is a pedestrian, and what that means, because it might differ a lot from company to company, and also from ODD to ODD, let's say. But still, this doesn't hamper. In this way, this doesn't limit the fact that we could still have a standard format to encode of this information and outsource the semantics to something like a open ontology that basically governs all the definitions and vocabulary there, and also enables reasoning applications. And then there's also a way to everything fits into the same, let's say, big vision of having a standardized and seamless flow from defining the ODD to inform data collection, produce ground truth according to specific formats and specific semantics, and then, let's say, also seamlessly close and bridge the gap with simulation by building cohesive, consistent representation in a language and a syntax that is digestible from simulation platforms, so that we also bridge the gap between the real world, the real sensor data world, and the simulated world in a very smooth, let's say, journey. This is the whole also idea that I want to convey. So since I'm approaching the end, I believe, this is just a summary of our initiatives from Deepen's perspective that we've done to build this vision of, let's say, common frameworks, common infrastructures, and also common databases that everyone can tap into to build better, safer and a more transparent autonomous driving system. So one has been the Safe Drive initiative that we've done with the World Economic Forum. We completed one almost a year ago now. And we created a data-driven policy framework for assessing the safety of ABS using this safety pool scenario library, which we just released this year. And at this point in time should be the biggest public scenario library available. Everyone can join freely and can tap into the scenarios, can contribute more scenarios, can share scenarios, and basically enable also regulators to have a window on what is happening in the industry. And basically, we also use that a lot with governments to inform and to build frameworks of the certification frameworks for based on scenario-based assessment type of approaches. Finally, last 2 minutes, I think. I just want to give you a summary of what we do at Deepen. So we take care of all the major steps that I talked to you about in the data pipeline for AI and machine learning driven development. So starting from calibration, which is our new product and which ensures multi-sensor data integrity with very deep multiple sensor modalities, LiDAR, camera, LiDAR, camera, vehicle, radar, and all the mix that you can think of. And we annotate the data, and we also validate the data and scenarios. These are our products and services, and this is basically our community initiatives, which we purely do for the sake of helping everyone, the whole ecosystem, in building better, safer autonomous driving systems. So it's Safety Pool initiative. You can take a look at it, safetypool.ai. And this is purely sharing data at scale, sharing scenario simulation at scale worldwide, globally, and talking to regulators to make sure that regulators also can design data-driven policies. And also all the standards that I talked to you about, which ensure the right interfaces and data models are in place for everyone to be productive with their data and share them and basically reduce bottlenecks in the whole journey. So I think that was mainly it. There was a lot of information, probably a bit compressed, but hopefully I got a little bit of the message. And if you have some questions, feel free to ping me also.
Thank you very much, Nicola, for the very insightful talk, and I'm sure the audience enjoyed it as I enjoyed it. I have no immediate question for you, but just want to remind the audience that you can post questions to the chat so that I can hand it over to the speaker after the talk. So thank you very much for sticking to the time and for your very nice insight that you conveyed with this talk. Let's continue with our next speaker in the meanwhile, which is Philip from Valeo. And as mentioned, it's about cyber physical systems. So there is some complexity in the physics and there is some complexity in the cyber world. And I think this complexity is rather multiplied than added. Yeah. And I look forward for contribution from Valeo. So Philip, the floor is yours.
You have to open the video for me, Bernard, if this is possible.
Open the video for you.
Yes, I cannot start my video, but I will start directly with the charts. That will be easier in this case. Okay, so I hope that you can see my screen, which is the first page of the presentation.
I can see it very well.
Yes.
Thank you.
Okay, very well. Thank you. So again, my name is Philippe Goujon. I work on innovation projects for Valeo. But today, my presentation is about another part of my job, which is about coordinating a large European project called CPS4U. And this project is dealing with the cyber physical systems and some work that we are performing right now concerning pre-integrated architectures. So what is this about? First of all, a first presentation about our project. The project is managed by the Excel joint undertaking. So this is a pre-industrial project. We are 36 partners from 5 countries. Our budget is 53 million, and we have 16 use cases which are being developed in our second, third, and final year of the project. 16 use cases involving partners from the automotive side, of course, including my company Valeo, but also colleagues from the industry and from the energy distribution domains. And on top of that, we have also SMEs contributing to the different use cases. You have here the references for our website, and we have also a LinkedIn group page. So first of all, cyber physical system, that's really the center of our work in the project. And this term, cyber physical systems, is not widely spread in the automotive domain. It is much more spread in the industrial partners, much more spread in the energy distribution, but not that much in the automotive domain, even if, in our opinion, the automotive developments and systems today, even more the connected and automated vehicles, are absolutely eligible to be called cyber physical systems, and even quite rather complex ones. So you have here an illustration that I took from a presentation made by NIST in the US, which is quite nice to describe the different levels on which the cyber physical systems are connected together, are working together. There's the physical layer, where you can see all the sensors or the actuators or the physical transformations happening. Then there is the cyber layer, which can be directly connected and integrated in the sensors or in the actuators, or which can be quite separate from them, like edge devices and things like that. And then there is another layer, which is really on the internet level, really services happening in the internet, connected, of course, to the other layers, but really on a different level. So it's quite a generic description, but which gives a quite generic description. And so basically everything which has sensors, actuators, a computer, some connectivity level, and some cloud computing can be called cyber physical systems. So to describe the landscape and what is happening in this for these cyber physical systems a little bit more in the automotive domain, there's a lot of complexity which is significantly increasing, especially in the field of the software development for these cyber physical systems, but not only. And this is the reason why today we are really at the limit of sustainability for the developments of these complex cyber physical systems, especially in the fields of driving automation. You can see here the curve on the left, which is significantly increasing. That's the dark blue curve. And the best-in-class software developers have a productivity increase, which is only the dotted blue line here. So you can see that the gap is really increasing. And without new solutions, without new processes, new methodologies, there will be really a shortcoming between what the market is expecting and what the providers, the technology providers, will be able to provide. So that's the first and the main reason for our project. Identify solutions to come back to a sustainability process. But there are also some important points which are evolving in our context. When we look at the new system architectures, of course, the Tesla is now a little bit the model for all the other car makers to provide really a centralized architecture with a few very high power computers managing the different processes instead of having distributed architectures like what we have today. So that's a very significant change. There's also a few new industrial players coming into that field. And there is an example on the right-hand side about some chipset makers willing to play in our field. And finally, the business models also are changing a lot, starting from new mobilities. Now we are in really at the center of the digital transformation and at the center of the smart city approach. So we are really, the ecosystems are really, have now a size which is much, much larger compared to what it was before. So is the curve going to flatten a little bit in the next few years? Probably not, in fact, because there are more and more expectations from the end users, from the society as a whole also. For instance, you have a list of new requirements which are going to come in the list very soon. Coming greener at the bottom, it's not. It's an illustration of the expectations, of course, towards more traceability, more CO2 neutrality, optimum usage of resources. That's additional constraints that our cyber physical systems will have to include, integrate as new constraints and new expectations. So what do we do when we are at this point? If you look at the illustration on the right-hand side, do we start to have a linear approach, doing everything from the top, going down to every bits and pieces of details at the bottom of the ecosystem? It's probably not the right approach. An approach that we recommend is to include new layers of intermediate developments or products that each of them being the result of the addition of what is coming at a lower level, so that we are more working in a networked structure compared to a linear ecosystem as seen on the left of the illustration. So basically, we are creating new levels. So it's not a new principle. This illustration is quite old. But what we propose here is to create what we call pre-integrated architectures, meaning that we want absolutely to reduce the R&D effort to develop these complex cyber physical systems. We want to reduce the time to market to be able to reach new customers and new domains. We want also to decrease the difficulty for SMEs to enter and to be credible players into these new systems. So this is what you can see on the illustration on the right-hand side. And during the project, we have put in place this ecosystem. We have put in place also several pre-integrated architectures. But the goal here is that a part of the ecosystem develops and pre-validates some architectures, and the application developers will use these pre-validated systems for their own development. So how does that look like applied to the CPS4U project? So you can see here our ecosystem using the partners, the 36 partners that we have with the CPS4U. At the bottom, you can see the basic modules, the components that we that we have developed, mostly with our SME partners. Then at the top, you recognize the applications, the automotive use cases, industry automation and energy use cases. And at the center, in the middle, one level that we have created according to our principle, which is related to the pre-integrated architectures. There are 6 of them for the needs of our project. I will describe them in 1 second. And also very important, on the right-hand side, we have several partners working on the tools needed for the developments of the components at the bottom, of the pre-integrated architectures in the center, and for the applications at the top. So that's our ecosystem. And I mentioned that we have 6 pre-integrated architectures developed in the project. It doesn't mean that any CPS in any cyber physical system just need maximum 6 pre-integrated architecture. But for the developments needed in our project, this is the footprint that we have defined. And this concept is very flexible. You have here a description, a schematic of very wide overview of the system architecture for the pre-integrated architectures that we are using. And you have illustrations of the prototypes that we have developed using the concept with the model at the top of the page. So basically here you can see the first one, which is a connectivity pre-integrated architecture. The prototype is available. It will be tested in the next few weeks, and later on, I'm sure that the partners that you see here will be able to put it on the market for the developers who would be interested. Then we have a second PArch pre-integrated architecture, which is related to computing platforms oriented towards deep neural network calculations and artificial intelligence, generally speaking. Then there is a third architecture, which is related to cooperative systems which are distributed quite widely on the ground, and for which a coordination, a cooperation is needed. You will see that this one is really working mostly in the cloud. Then there is an industrial edge computing gateway, which is a mix of computing and connectivity and adapted to industrial applications. And then finally, two architectures related to sensing, one which is more oriented towards perception of objects around our vehicles or around our robots that will use this architecture, and another one which is more related to the localization of the vehicles which will be using the prototypes. So you have a picture of the connectivity architecture on the right-hand side. On the other page, you have here an illustration of a prototype coming from Calray, which is an 80-core computing platform. And this platform has been developed according to the principle at the top, but of course the tools and the instantiation here from Calray is specific to this industrial partner. Other instantiation and other prototypes are available from other partners, but I'm just giving examples of real prototypes which are being developed. Then concerning the industrial edge computing gateway, here you see that it's really a standard box using connectivity with sensors directly integrated on the machines on the shop floor, and on the other side, this architecture is communicating with the cloud platform to perform some services that we will see on one of the use cases later on. And this one, again, that's one of the prototypes using this gateway, but the prototype is developed by Eurotech and Leonardo in Italy. Concerning the cooperative systems of systems, this one, I will explain the use case later on. You will see very easily what is the purpose of this server here on which the virtual machines are running. And on the right-hand side here, you have an illustration of the sensing, perception, and localization architectures. And again, prototypes developed by Valeo inside the project. That's not the only one which are built upon the architectures, but that's one illustration here, showing some sensors, generic version of sensors coming from Valeo, and a generic version of the Deep Manta software developed by Valeo and CEA, providing pixel segmentation, bounding boxes of objects, etc. What are the use cases? And that's, I will finish in 2 minutes. As I said, there are 16 use cases in the project, and some illustrations here for 4 of them. So Valeo is developing use cases mostly oriented about artificial intelligence for the perception of objects. A second use case is articulated about the question of localization. And here there is a lot of cloud computing also, which is taking place to aggregate all the data coming from the different vehicles equipped with the recording devices. And finally, there is a consolidation of these 2 previous use cases into an urban driving use case, which will be performed in June next year, June 2022. So that's for the Valeo part. Concerning the industry automation, here, as I explained earlier, they collect the data directly on the machines, which are performing the trimming operation in one of the assembly plant at Leonardo, and they send the data in the cloud to do some analysis and modelization of the trimming parameters, issues happening during their operation in the plant. And then this model is sending back the data on the shop floor to implement the optimization, the improvements on the trimming parameters in the plant. And then finally, an example of coming from RTE, which is the French energy distribution network. They have an energy loop, which is a test bed for their new developments, which combines traditional nuclear energy power plants in France, but also wind machines, also solar energy, and batteries. And their goal here is to avoid the peaks of intensity when all the energies the plants are producing and the request for energy is low. There are risks of high intensity, and they need to cut the grid for some time. Using their model coming from the collaborative architecture, they can anticipate all the peaks, and they can switch very quickly on the ground the different lines, the different power lines. And for instance, when there is too much power produced, they can create a derivative towards the batteries, which will accumulate the energy in excess. And there's a very significant business case in doing that. Instead of wasting energy, they will make an intelligent processing to optimize their power grid. So as a conclusion, so in the project, we are putting in place solutions and possibilities to reduce the R&D efforts that all our companies are facing today for the developments of cyber physical systems. And it's really a practical approach we do not want to be too theoretical or too far from the reality. We are really building these architectures from the ground up, but of course with the constraints coming from the new challenges expected by end user and by the society. We are working in a networked ecosystem. That's very, very important. So we work differently compared to what was done before, and that fits quite well with the needs coming either from large companies like Valeo, but also from SMEs. We have several ones already showing some products, and also from the tool providers. So please come to visit our website and check the deliverables which are available and the presentation. And if you want to contact some partners, please do not hesitate. If you want to buy new sensors, for instance, state of the art, if you want to buy a connectivity device, again, state of the art from Thales, please contact us and we will be happy to discuss with you for potential applications. Thank you very much, and back to you, Bernard.
So thank you very much, Philip. You mentioned networked ecosystems. That brings me immediately to the next call. So we not only have technological ecosystems at the infrastructure or data sharing level today, but when it comes to mobility, we are also transitioning to a kind of ecosystem that even involves some change of user behavior. Yeah? And therefore, it's a pleasure for me to announce our next speaker from the University of Modena. Roberto will tell us something about autonomous vehicles and in the context of smart cities in the Motor Valley, this being a contribution from the mobility group in the PDVA. So Roberto, I very much look forward to the insights that you will give us today, and the floor is yours.
Thank you very much, Bernard. So I'm going to share my screen, and I hope you are able to see. So, thank you very much again. My name is Roberto Cavicchioli, and I'm a researcher at the University of Modena Reggio Emilia, and in particular, I am part of the High Performance Real-Time Lab. This lab is a university research lab which is focused mainly on high-performance real-time systems. We are about 60 people and increasing during the years, and we work mostly on the most advanced embedded computing platforms that are available on the market, and not only that ones, because we have also some samples of new kind of architectures to facilitate autonomous behavior for different applications, such as obviously cars, but also drones, water or underwater devices. And what we usually do is we develop hyper specialized software application that runs on a real-time operating ecosystem. So we have a lot of industrial collaboration with some of the Motor Valley car makers, such as, Maserati, Ferrari, and so on, but also with technology providers like NVIDIA, Xilinx. Also, we were able to receive funding from the European Union within the Horizon program, as the previous speaker was talking about. And I will describe during my speak what we were able to achieve within the two projects, Hercules and Class, and what we will achieve thanks to the 5G Meta and G-Cloud project that we have. So, with respect to the complex and workload-intensive tasks that are needed for an autonomous car, such as have been already described previously, like perception of the surrounding environment, path planning, a lot of machine learning and deep neural networks that need to coexist within a strict latency critical control and activation loop, because we have to drive a car within deadlines, within hundreds of milliseconds of readiness, okay, even less. So in the Hercules project, we deployed these tasks on an NVIDIA Drive platform, which was at that time based on the Parker system on chip, and we had to keep latency under control and to reach predictable performance by means of a lightweight hypervisor that we modified to reach freedom from interference with respect to the memory resource. Because also another issue that we found out is that when there are a lot of engines that are requesting memory, the issue is not only in the latency of the task, but also in the latency of retrieving the data which you have to work on. And the result of the project were tested on a real Maserati car with elaborating sensors that were like LiDARs and cameras, but only on an NVIDIA Jetson TX2 developer kit, which was exactly the same architecture system of chip of a traditional, let's say, NVIDIA drive at that time. With this low power device, we were able to obtain precise localization and mapping, as you can see here. This is the map of our campus, and has been reconstructed using what is called a SLAM, simultaneous localization and mapping algorithm, that runs entirely on the selected hardware. You can also see that the car chosen path in front of the vehicle, so to choose which is the path of the car and predict what will happen next. Nevertheless, detecting road users in real time is the key to enable safe autonomous driving application when we are in a crowded urban environment. The perception and planning in these kind of scenarios have increased difficulty due to the fact that obstacles, occlusions, the high dynamicity of the system in which we are really increase the bar for the level of complexity of the system. So to test and to verify the urban capability of the algorithms that we deployed, we collaborated in the creation of MASA. What is MASA? MASA, or the Modena Automotive Smart Area, is a living lab created to develop, test, and validate all the automated and connected vehicles that we worked on. It is a public-private partnership that offers OEMs, Tier 1, Tier 2, an environment to develop and validate the solution that they deploy for cooperative connected automotive mobility. In particular, in this area, there are tens of smart cameras supporting embedded computing platform for edge-side real-time detection, and they are connected in a fog computing paradigm by means of a low-latency V2X communication. Therefore, MASA is an open test bench where interested partners may deploy and test what are the next generation of autonomous driving and ADAS application in a tightly connected settings. The building of MASA has been not only founded by the municipality of Modena, but also from the European project class, which has finished just in the middle of 2021, and in which we deployed an innovative distributed software architecture able to run on a compute continuum of edge, fog, and cloud that meets also real-time constraints as an objective of the project. In this kind of infrastructure, the car is seen as a mobile sensor, and together with the edge nodes, they elaborate the video streams for detecting the road users in real time. Then only metadata is sent to other vehicles and cloud by using a low latency V2X communication media, and then these metadata can be used in many different scenarios. Just be aware that if we consider an autonomous driving car or a car that has so many sensors, such as 4 to 6 cameras, a couple of LiDARs, a lot of radars, and so on, it can create about 300 terabytes of data per year. And all the traditional cameras that are on the territory of Modena are meant to send high resolution frame to what used to be a centralized server infrastructure. Now, the other thing is to use smart cameras, because we are able to elaborate the enormous amount of data that these cameras are recording on the edge. And the communication media that we exploit are a private 4G network and some DSRC antennas. And we are able, without the traffic generated by the usual huge amount of numbers of users that connect to the antenna of 4G, to obtain performances that are near to a 5G implementation, let's say. So we have latency that are reduced within 10 milliseconds, and we have the possibilities of having not only vehicle to vehicle, but also vehicle to infrastructure communication. And to maintain the data exchange small, we developed our own communication protocol. As already said, everyone usually tends to create its own paradigm to represent the reality that is around itself. What we did was to keep this very tight and short to be able to send a lot of these packages in a very low time. In particular, the idea is to send the metadata in a datagram over UDP, so to be the fastest possible, and with the structure of the message to be reduced as possible. So we can define the position by means of latitude and longitude of every object in the area. By object, I mean every road users, car, pedestrian, bicycle, bus, and so on. Its speed, its orientation, and the category of the object. So we are able to provide a snapshot of the whole city, okay, or at least for the whole area covered by the cameras. On the edge side, as I was saying, we have multiple cameras that are able to detect road users and potential obstacles for the smart vehicles. And we run deep neural networks and we detect all the vehicles and so on. And therefore, we obtain a consistent representation of the road users with their position of the massa. And we obtain this in real time, and therefore we have a digital twin of the area. Please be aware that, as I said before, the maximum latency allowed to compute the snapshot of the area is 100 milliseconds. Should be below 100 milliseconds, because otherwise the autonomous system on the car is not able to react fast enough for not colliding, let's say, with another car or another user. On the other hand, on the cloud side, we gather all the metadata that we obtain, and we can use this metadata to enhance the monitor capability for the municipality and the police as well. We can have a real live map that is updated every second, and we are able then to provide a very tight reaction to every possible urban hazard, or to plan, let's say, some green routes for emergency vehicle to run, or ambulances or firefighters and so on. And the historically aggregated metadata is also useful for other use cases, let's say. Just to give you some example, we can derive traffic prediction for different kinds of road users. We can create datasets for learning and predicting the behavior of the road users. So in order to increase the capability of the autonomous driving algorithm to run and so on. It is important, nevertheless, to mention that all the data that we are gathering is only metadata. So it's compliant with the European GDPR to maintain the utmost capability of privacy of the citizen. Here, for example, you can see an example of the analytics that is running on a video stream on a street camera. Each road user is detected, and its position is computed by means of a calibrated homography on the particular view of the camera, and then there is a tracking. The information can be seen on the lower map, on the lower corner, and each color corresponds to the road user that is detected in the video. So with this, we are able to provide services to the community and the municipality. And the 5G Meta project, in which I'm also involved, targets the monetization and the capability of creating more and more services, such as this one, or let's say to provide something like I want to have all the information of all the objects that I'm around in this area, and I can provide a service on licensing or on a, let's say, on a period in which I will have to pay for this service or retrieve all of this kind of information. Unfortunately, we are not able to change the traffic light for, let's say, trying and create a green route for an ambulance or a firefighter. And to verify the impact that the smart and connected vehicles are able to provide the traffic of the area, we use the metadata to feed Matsim. Matsim is an open source simulator for transportation, and we enhance the software to be able to interface with the metadata that we obtain from the MASA, and we model the misbehaving of the driver to compare the number of accidents that could happen with or without the capability of communicating this information to the cars. And if you can see here, we represented like 900 agents, which should run, okay. And these are independent traffic flow, and each agent can be a car, traditional or connected one. And the benefit we have from the data that is gathered from the city is that we simulate exactly what happens with a digital twin of all the objects that are in the city. And we have seen that we can have a 35% reduction of the time needed for an ambulance, for example, to reach an emergency site if the car are alerted not only by the sound of the ambulance itself with the siren, but also with a message sent by the infrastructure itself. So I will thank you for your attention, and I have just a small presentation video. And that's it. Thank you very much.
So thank you very much, Roberto. Very interesting talk. I think we have had a series of talks now where we could see what is happening right now in our industry. The cars are getting autonomous, cars are getting much more connected, yeah. Cars are getting electrified, and there is also the vision, I think, of sharing the cars in the future. That is about the mobility aspect. So all of that together somehow poses some challenges, and there's a topic that is accumulating all these ideas about connected, cooperative, and autonomous mobility. And our next speaker from Ertico is Stepan, and Stepan will tell us today something about the challenges of the future, our research and innovation needs when it comes to data sharing. I think some kind of data sharing we have seen in all the talks. So I very much look forward for your contribution, Stepan.
Thank you, Bernard, for the introduction. So I hope you can see my screen. Trying to put it full screen. Yep.
Perfect.
Great. So good afternoon. So it's a pleasure for me to participate in this session, which is on a topic that is really at the heart of both the Ertico activities and as well the arcade project, which I'm coordinating. So I'm Stefan Dreher, so I'm Senior Manager Innovation and Deployment at Ertico ITS Europe. I'm working more specifically on connectivity, automation, and blockchain topics. And as I mentioned, I'm coordinating the Arcade Support Action funded by the European Commission, and which is aimed at coordinating research and innovation activities in Europe. I'm also a member of the CCAM Partnership Executive Group, where I'm leading Cluster 7 on coordination. And I will present today a bit about, as you mentioned, these challenges on CCAM, and in particular, the data sharing framework that we developed, and also the related work in the CCAM partnership, and also about the outcome of one workshop we organized on the data sharing topic earlier this year. So quickly, what the typical use cases for data sharing in CCAM. So a lot of data is generated in CCAM in general through the sensors, and it's really essential to drive the innovation. Regarding testing in particular, the collection of data is really essential for further technology development, assessing the safety and performance of the technologies, and also analyzing the impacts. The issue that we have been looking into at the beginning of the Arcade project is that many diverse tests are ongoing across Europe, and coordination is needed in order to have a synergies between these different tests. And in general, significant resources are really spent in collecting the data, but and then there is not much left actually for analyzing the data. Therefore, we should really push to reuse this data as much as possible. And something preventing it is, for example, the lack of funding at the end of the project. So generally the databases are not necessarily maintained. There's a lack of proper meta description, lack of using standards, as was already mentioned as well by Nicola. So I think there's a lot to be done here. And now as well, we identified the need to look at further CCAM specific use cases requiring non-competitive data sharing, for example, more specifically for safety and validation. So the CCAM platform that was set up by the European Commission and that concluded at the end of last year had a specific working group, the working group 2 on coordination and cooperation of research and innovation and testing activities that has been looking into this topic. We looked at challenges, priorities, and requirements for test data sharing framework. And there was a conclusion paper prepared that identifies the let's say, the scope of what could be a European test data sharing framework. And then, as part of the CCAM partnership, which has been recently launched in the frame of the European Horizon Europe framework program, there we have several clusters working on or looking into topics related to data in general for CCAM. So in particular, cluster 5, we're looking at the key enabling technologies aspects and also industry data sharing, while cluster 7, where we have been looking more on the test data sharing aspects. And more recently, we have been working as well more with cluster 3, which is building a scenario database, or at least we are defining the needs for it for the future work program. And cluster 4, as well, looking into the digital twins and traffic management aspects, where also data sharing could contribute to. To support the different projects in data sharing and really enable this further in research and innovation, the Arcade project has been looking into a data sharing framework. So this actually has been developed in previous projects, starting already a long time ago with the FOT-NET projects, which developed this data sharing framework together with an impact assessment framework. This data sharing framework is now part of the knowledge base, which we have developed in Arcade, and which is online and available and accessible at the link I indicated at the bottom. So the current knowledge base is meant to be a one-stop shop for all information related to CCAM initiative in Europe and beyond. It contains an overview of research and innovation projects, EU-funded and national ones, but as well an overview of regulations, policies, strategies, roadmaps, standards, evaluation methodologies, and finally, this data sharing framework. As part of this data sharing framework, the aim is to support projects and organizations by giving really hands-on recommendations in different topics that are really important to enable this reuse of data and data sharing. The framework is really focused on field operational tests or naturalistic driving studies, but it has proven to be useful as well for other domains. Some parts are related to the early phases of data collection. For example, giving examples of pitfalls to avoid that later can make sharing or reusing data sets difficult or even impossible. So there are, among these boxes that I'm representing here on the left, there are 5 administrative topics relating to agreements and contracts, training material, application procedures, support and research services, and as well financial models. The 2 topics at the bottom are more practical and data-centric. So the data and metadata description outlines a model that has many different aspects of describing the data. So not only the actual raw measures must be described, but also all the derived measures, file formats, and also the context in which the data has been collected. Then there's also a section on what is considered to be more the data protection, so GDPR issues, which I will a bit detail later in this presentation. At the moment, what is in the making is we want to focus now more as well on data formats to make them really interoperable, and providing overview of the many other initiatives, in particular the L3 pilot data format, scenario databases, edge cases, simulation-specific formats, etc. So just to mention that this is constantly in evolution, the framework is currently being revised, and you are, of course, welcome to provide comments and propose changes or addition and contribute to it. The idea is really to have a comprehensive online free database that enables us to share best practices. So, So what has the idea of this data sharing framework, of course, needs to evolve, and that's why now in the CCAM partnership, where we have developed the work program for the next upcoming calls in CCAM in Horizon Europe, we have been looking at the next steps to make this framework evolve. As I said, the data sharing framework so far consisted more of hands-on recommendations. It has a strong focus on field operational tests and driving studies. And it was more support material for setting up data sharing. In the last calls that have recently closed, the idea has evolved into really creating a first federated CCAM test data space. So building on existing platforms like the IDSA, like the Gaia-X framework, in order to really focusing on more broadly facilitating test data sharing and implementing as well really on existing software platforms. And now the vision we are working on, in particular with the other clusters, is to go towards a CCAM data space, because we believe that it's very important now to include as well, not only test data, but really look into tools that have been developed for CCAM in other clusters. So for example, tools for data processing, data capturing, the descriptions, annotations, and so on. Then we also would like to make the link to other data spaces. And then here we also believe that it's important to make the link to data providers and data users. So that's still being developed. It will be considered in the upcoming work program for 2023 and 2024. Then, as part of our activities in Arcade, I mentioned we organized a workshop recently. I mean, recently, it's now quite some months ago. It was actually early 2021. And the idea there was to really exchange best practices among different projects that have been dealing with data sharing, as well looking at some examples from industry, and also looking at the different initiatives that are currently being developed. So there's really a great momentum at the moment for data sharing. I mean, there's the European Data Strategy. There are platforms like Gaia-X, the International Data Space Association. And I added as well now to more recent initiatives like the Mobility Data Space and the X-Road projects, which we didn't look into in the workshop, but okay, I think we add it here because it's important to still look at that and to make this vision and the identification of challenges evolved. I mentioned we also looked into some practical experience with data sharing in large-scale projects. And we looked into specific cases here, for example, for road safety that was presented by ASEA. And here, because the road safety data ecosystem is really one key component addressing road facilities and accidents in Europe. And the whole ecosystem that this SRTI ecosystem builds is really a very, let's say, state-of-the-art and good example of good practice. So it's based on cooperative and decentralized approaches where you can access the different messages if you also contribute to it, and where each participant in the system takes on a defined role with clear formulated obligations. We also discussed this the edge computing lab example from AI Sweden. There's also very interesting discussions on that, and where we in particular addressed the challenges of edge computing, which is used as well in other domains, and where we can learn from in the automotive sector. And then we looked at practical examples from projects like UDrive, Autopilot, and L3 Pilot. And I just would like to give a bit more details on that. So here projects have been really sharing very interesting approaches, in particular regarding sharing of data between partners of large-scale projects. That's generally already a very important challenge. And we have seen different approaches there to solve the challenges and the issues. So for example, the UDrive project, which was a large-scale naturalistic driving study running from 2012 to 2017 with more than 120 cars and 40 trucks. And they have developed an online monitoring tool really to keep full control over the data and being able to keep track of everything, including vehicles, but also data loggers, encryptions, and so on. And this iterative approach that they mentioned it was really appreciated there and useful for all the experienced analysts. Similar in the Autopilot project, which was running from 2017 to 2019 and focusing on how Internet of Things can support and improve actually the performance of automated driving systems. And there it was mentioned that really it's important to ensure good communication between the data collection sites and the different analysts by in particular defining logging guidelines and common data formats, file formats, and naming. Automating the data validation process was also highlighted there. And then finally, the L3 Pilot project, which is really was a flagship project funded by the European Commission with more than 12 European car manufacturers, and that recently concluded and is being continued in the follow-up project, which is called HiDrive. And there they developed a common data format that made it really possible to commonly work with all the partners on one tool chain. And that's very, very important highlight. So we are also detailing this common data formats into our framework. Finally, as I mentioned, we also looked into principles for industry data sharing, in particular with some initiatives like the Enrichment data ecosystem. We also looked into projects like the PUMAS project from the TNO, and also looked in the workshop at different initiatives outside of Europe, like, for example, the AV test initiatives from NHTSA. And there, some of the main outcomes were that for every project, it was really highlighted that it's important to define conditions for sharing from the start of the partnership, and to, in particular, publicly disclose what data will be collected in the project. And as a consequence, it's important to inform the data user about why the data was gathered and what the data can be used for. So that will prevent you from having issues afterwards for reprocessing and reusing the data. Regarding anonymizations, as well, we looked into that it's important to translate the raw data into scenarios and labeled driving sections. However, for a full system assessment, more information is obviously needed. And there it's very important to have this trade-off between pre-selecting the signals and the data within the car, and the risk of eliminating future research questions. So that's a very important aspect now, in particular regarding edge computing. As we want to already process some data in the car, we really should clearly define in advance what data will be processed, how it will be reduced in the end, because once it's done, we will not be able to go back and make more data available than in the initial planning stages. Privacy was also addressed extensively, and then one interesting point was also mentioned to deal with the findings from that impact public safety. So it was mentioned that it could be interesting to have an approach a bit similar to the software vulnerability exposures that is used there. I will be very quick about this part. So this is really widely discussed. I mean, but here in our discussions in Arcade, we wanted really to look into practical examples with data sharing and GDPR in particular, because several projects mentioned difficulties where some partners were really reluctant or refused to share data, citing GDPR as the reason, and therefore we wanted to look at why this is the case and how this can be improved. So some points that were discussed is, for example, the use of regulatory sandboxes. So that's could be a place where we could just test a material and data collection before it's actually put into work. So we did not really discuss now the details on how to implement it, but it was just a concept already that it would be good to have the data authorities already supporting this kind of sandboxes in setting up these frameworks instead of just then going to fines in the end. We also think that it was extremely important to work on this participant consent chains. So the data subject, as I mentioned, should be in control over where, who, when, and for what purpose his or her data is being used. And it's important to introduce processes for communicating the updates with regards to processing personal data. We also looked into research exceptions. So it emerged that this topic is of much interest, but it's not well understood and actually underutilized by academics and researchers. So here it's important as well to share best practices about when this research exception can take place. We also then discussed legitimate interests. So that's linked to research exceptions and ethics. So proving that you have the legitimate interest in using the data. And finally, we also looked into data minimizing technologies. So here interesting could be, for example, to have more research on deep fakes, because that could allow you, used in the proper way and used in this particular case for a good reason, to actually replace the identity of some testing subjects and facilitate anonymization. And I think that's more or less my last slide. So just to quickly summarize, some of the outcomes of, in particular, this last workshop, but as well some of the things we are looking into as part of the data sharing framework. So it's essential to look into standardization of metadata, and regarding CCAM in particular for operational design domains, scenarios, functionality, and services. We need as well to look into the requirements for data sharing in real time and for in-vehicle selection of data. So here I mentioned the case for edge computing, about really selecting from the start the right data for the right purposes, as it cannot be changed afterwards. We need to formulate an easy and understandable approach for organizing participant consent and consent chains. Mm-hmm. And finally, we need to define an approach for balancing between the public interest and industrial confidentiality. So here we really need to think about these win-win models. So for both the public authorities, but as well the industry players beyond the competition. I mentioned this regulatory sandbox approach, the common vulnerability and exposures idea, and and then, as I mentioned, for GDPR, we need to have more sharing of best practices and then further explanation of practical use of this to enable data sharing. So that concludes my presentation. So thank you very much for your attention.
Thank you very much, Stefan, for this insightful talk on data sharing. I mean, I think it's really becoming a topic that is getting more and more momentum. Yeah. As you mentioned that you are also working on this blockchain technologies. The question was popping up to me as there is so much activity around Gaia X at the moment, and IDSA that you mentioned, that is, so to say, the European way of building up data sharing strategies. And if you look at initiatives like the Mobility Blockchain Initiative, MOBI, I was thinking on, how do you see the relationships there? Can the one approach integrate the other? That is actually a very posh topic, and I want to give you that question. What is your thoughts about that?
Yeah, indeed, that's a very good question. So we have been looking. I mean, as part of my blockchain activity, so I'm chairing the mobility working group in the INATBA association that was set up by the European Commission. And there, indeed, we have been more investigating how blockchain can support, in particular, mobility use cases more broadly and enable data sharing. And what I'm a bit surprised about is now, of course, I've seen many of the projects that have been mentioning in the decentralized approaches. I mean, we have some platforms as well that we are working on at Ertico, in project that we are involved in, like Phoenix and others. And there we are looking into decentralization, but we are not necessarily looking at blockchain approaches. And therefore, I think it's interesting to have these synergies between these projects that are running, but then as well organizations like INATBA, but as well as you mentioned, MOBI, and see because there are still several challenges as well regarding that. I mean, interoperability between chains, the interfaces, how to scale them up, and so on, and here as well. I mean, I'm always coming back to the need to share best practices. I think it's very important to see what are the applications already out there building on distributed ledger technologies, and what, from where we can learn, and that can be applied to mobility. And not only automotive, but really we are looking at Ertico in particular at the more broader mobility, so mobility as a service, actually.
So thank you very much. We can probably discuss on that a little bit offline then after the meeting. So we are running out of time. So therefore I am quickly handing over to my colleague Oyana from Wicomtech Foundation. Handing over to her. I think she will give us a little bit of insights on CCAM and say a few words on that, and then conclude the session. So Oyana, the floor is yours.
Okay. Good afternoon. Thank you, Bernard. I'm trying to share my screen, so hopefully you are now seeing my PowerPoint presentation. So yes, I am Oyana Taegi. I am the director of ITS Engineering Department at Wicomtech, which is a research institution, and I am co-leading with Bernard this automotive session on the automotive subgroup at the BDBA. But today I am here just to quickly present the CCAM partnership. I will try to be quite fast because I have a couple of minutes. I think that Stefan has already mentioned some of the important things that I was going to comment, but I think, or I am going to highlight my 2 minutes, just focusing on the importance of this European partnership and how to collaborate between the different partnerships and actions within Europe in order to commonly build technology that is somehow providing Europe the unique opportunity to consolidate somehow the leading role in not only ICT, but also in the specific sectors when applying these technologies. So you all know that the European partnership are somehow key implementation tools that contribute or will contribute significantly to achieving the European political priorities. And somehow the CCAM partnership and the reason why I am presenting this here is that mobility and the automotive sector somehow is evolving. and is crossing somehow a new digital frontier, allowing the vehicles to communicate with each other. So we have seen that in today's presentation with road infrastructure, with other road users, and this will enable a coordination and cooperation between road user, managing traffic, mobility at the interior level, okay? So somehow we need combining connectivity, we need cooperative system, and the automation will enable somehow automated and fully orchestrated maneuvers. And we will try to have this, will bring us closer to this vision zero, okay? So we know that we have a lot of challenges in front of us. We know, we are aware that the society does not yet demand a transition to the CCCAM, which is connected, cooperative, and automated mobility, since the potential implication and benefits of the integration of this kind of solution into the mobility system have yet not been demonstrated, or the end user is not fully sure of what is going to be expected from this. Also, the technological capabilities to cope with the increased complexity of what the CCCAM is demanding from the technology side to be able to develop and provide a useful solution is not sufficiently mature. Somehow also we need somehow to build the complete CCCAM solution and fully exploit the societal benefits. We need somehow a cross-sectorial value network, and this will somehow require a transparent cooperation among local, regional, and European authorities, and also the private sector. So in this sense, and I am not going to go into detail, but in order to cope these challenges and help Europe to keep be a leading region regarding mobility, the CCCAM partnership has been divided into clusters. So Stefan has shown this figure, but I would like somehow to make some comment regarding the cluster and their activities, because I think that is important. So the first cluster is somehow dealing or somehow focusing on larger scale demonstrators, which is somehow to ensure that the results of all other clusters are capitalized and implemented into large scale demonstration in pilots to support the deployment readiness and to show the final end user the impact of those implementations. The cluster 2 is leading with specifically vehicle technologies, so aim to deliver the most efficient and effective future solution, which should be proven safe, reliable inside the vehicle, and somehow try to do some kind of significant technical research and innovation challenges in the technology that the vehicles require. The cluster 3, Stefan mentioned, is about validation. So somehow, which are the procedures, which are the methodologies and tools that are needed for validating, verifying, and rating the CCCAM systems, whatever they are. The cluster 4 is more on the integration of the vehicle in the transport system. So somehow it's not only about the vehicle, it's the vehicle into an ecosystem, and somehow how to cope with the digital infrastructure. Cluster 5, which is somehow dealing with key enabling technologies, and this is why I am talking here, because we have seen that artificial intelligence, big data management, cybersecurity are key technologies that were somehow previously not so demanding in the mobility and automotive sector, but now are a requirement, and we believe that they will support the whole mobility system, consisting of vehicle technologies integrated in the vehicles and in the transport system, as well as the validation of all aspects of the entire system. The cluster 6 is about societal aspects and user needs. We only need to take into account what society is asking for. It's not only about the development of technology itself. And finally, what Stefan has just presented, the coordination, which is coordinating all stakeholders and activities and facilities. So I am not going to go through all these slides, but I would like somehow to make some kind of focus on this one, because we think and we see that for further strengthening synergies and complementarity at the European partnership, we need somehow to build some kind of cooperation. And we see the same as we are integrating ICT technologies, that we need to build some kind of cooperation with other active partnership. And we are seeking of coordination and alignment with not only data and AI, but also 2.0 photonics, HPC, and other initiatives, without forgetting the rail sector, which is also somehow going through similar exercise and facing similar challenges. Regarding key enabling technologies, and this is where we see that is a close cooperation with all the activities that has been discussed in BTBA, in AI, and in this workshop. So somehow we are trying to provide AI and cybersecurity solution to be integrated in the vehicle ecosystem, and try to somehow include the AI and the data in the validation, and somehow provide some kind of harmonized procedures and methodologies and tools to validate that. And somehow we are promoting how to integrate those key enabling technologies in the whole chain. In this sense, the main actions that we foresee in our cluster somehow are going to be the inclusion of cyber-secure components and systems, and how to include them in the CCCAM ecosystem, the robustness and the resilience, the explainable concepts and the training of AI in CCCAM application, AI for situational awareness, and system architectures for data sharing. So somehow we are demanding technologies that are being implemented in cluster 4, but are going to be exercised in cluster 5 in a very specific sector, which is mobility and automotive. So that's why we think that it's key important to somehow cooperate and build this kind of cooperation between partnership and activities that are being done at the European level. And I don't want to explain further. You have all this information in CCCAM partnership website. So please, if you have any question, visit that, or just somehow send me an email. Thank you very much.
I see. It was an accident. We are still live, so I was hearing nothing. So let me conclude the session and say a big thank you to all the speakers. Yeah, we had an online meeting this time. Thank you very much for all your valuable contributions. Yeah, I hope you could enjoy the meeting as I could enjoy it, and I look forward to meet you. We look forward to meet you in face-to-face another time. So thank you very much for your time that you invested in that, and once again for the great speakers that we had today. And with these words, I'm going to conclude the session. Thank you.